Welcome. Appreciate everyone attending. I recognize also I'm standing between everyone and beer, so I do appreciate your attendance, and hopefully it won't be a bad investment on your behalf. So my name is Spracklen, and today I'm going to be talking about operationalizing data science using Cloud Foundry. So I currently work at Alpine Data, which is an advanced analytics startup headquartered in San Francisco. And basically, we focus on building out advanced analytic software that delivers end-to-end solutions in the enterprise space. So this is actually part of what we deliver, which is a sort of code-free visual framework for actually building out analytics flows, be that on top of Hadoop or databases or what have you. And the nice thing about this is it allows the data scientists to focus on the problem. They can build out these analytical flows in a code-free manner and not have to worry about how this is mapping down to the execution framework under the hood. Is it going down to Spark? Is it going down to Hive? Is it going down to Flink? They don't need to worry about, how many executors do I need? How many gigabytes do I need per executor? Rather, they focus on their domain problem. And then under the hood, Alpine is basically going out and querying the cluster, figuring out the size, the configuration of the cluster, the topology of the cluster, the utilization of the cluster, and then using all of that information to, in real time, come up with an optimized execution plan. And so basically, I think it's a lot more efficient process than binding to the execution framework and exposing the data scientists as sort of the nuts and bolts of big data technology. The other nice thing about this as well is it really does future-proof your analytical flows. If you think about the rate at which big data technology is evolving, right? There's MapReduce, Pig, there's Hive, there's Spark, and recently we saw Spark 2.0 get released with a whole bunch of new APIs that we have to contend with. And so if you're not careful, basically you're constantly having to go back, update, port, modify to keep your analytical flows abreast of sort of that wave of technology. Whereas with Alpine, because we've introduced that sort of abstraction level, this remains relevant, and then under the hood, we're basically making sure that you're mapping down to the most relevant execution framework. All right, so let's talk a little bit now about operationalization, right? I mean, pretty much every enterprise company today has a Hadoop data lake. Everyone has a big data strategy. Everyone has a team of data science PhDs that are mining that lake for sort of actionable insights. Basically, we're pulling all of the data from across the enterprise, dumping it in the lake, and then these guys are basically sifting through it and trying to figure out something, how do we optimize for cost? How do we, score our sales leads better? How do we sort of better target our marketing strategies? And so there's a lot of focus, there's a lot of technology being built in this space, there's a lot of software being built in this space, but the lion's share of it really is focused on allowing these data scientists to run ever more complex models on ever bigger data sets. And so, if you want to basically, do deep learning on terabytes of data, there's a bunch of libraries out there to support that. If you want to build a sort of complex, sophisticated ensemble on a terabyte of data, again, there's a bunch of libraries out there to support that. And that's critical, right? I mean, it's a necessary part of our evolving big data strategy that these algorithms get and implementations become more performant. But I think we sort of a little bit myopically focus on that component and don't think really about what happens after the model is created, right? So we have these guys that are basically analyzing the data on the data lake in Hadoop. They create this predictive model. And then what? How does that actually translate into the broader enterprise, taking actions and delivering cost savings or benefits to consumers based on that model? Quite often, I've seen a lot of good analytical projects being run, and then they wrap up with a presentation or a PowerPoint or an Excel spreadsheet. And people sort of look around, job well done, and then everyone goes their way. Nothing happens, right? And so a lot of these insights are just sort of dying on the vine, so to speak, because there is this sort of barrier to basically operationalizing the results. And this is largely because if you think about it, where do these models need to be used? Well, they need to be used much closer to the end user, to the consumer, be that an internal enterprise consumer or an external consumer, right? You want basically, say, Salesforce apps to be able to tap these and leverage the predictive insights. Marketo, if you're building web apps, they should be calling out to it. If you've got a mobile app that's, for instance, is users calling in and trying to figure out how to rebalance their 401ks, you want that to be sort of leveraging these predictive models that you've built. And it's just not a viable strategy to think that basically from externally to a large enterprise company, you're going to be able to punch down to your Hadoop cluster and run on that, right? This is where the predictive models are trained. This is where they reside at present. And yet there's this big separation between where they actually need to be to deliver predictive action. And so, as I said, this operationalization is the weak link. And I think in a lot of cases, it is preventing enterprises really seeing the benefit and the actionable insights from these analyses that are being created. In some cases, I have seen situations where basically the data science will create the model, and then a separate team sort of quote-unquote operationalizes it, which is really taking the algorithm and building it into their various business logic solutions. That is potentially very error-prone. It's very costly. These guys are using, say, Spark ML lib over here. There's no analog on this side of the house, so how do you basically sync up and make sure it's doing the right thing? In a lot of cases, we're finding that these guys will train a model, and then 6 months later, it's going into production. That's a pretty stale model by then. So what are these barriers, right? How do we start to knock them down, right? Essentially, we're training these predictive models in batch mode on the cluster, and then most of the consumption of these predictive models, is more in a sort of streaming, real-time sense, potentially subscribing to a Kafka stream, JMS flow, or potentially just building a standalone sort of RESTful scoring engine that can be queried in response to incoming user requests. And so the first problem, as I said, is basically breaking out the model from the sort of confines of the data lake, then converting it such that we can actually perform streaming on that. And then also the questions become is how quickly can we update the models? If there's a Herculean effort to actually get this into production, it's going to occur very infrequently. And so you're going to have a very stale model that really prevents you from sort of exploiting a lot of the sort of nuances in your data stream. It also impacts your agility and your ability to respond to sort of new market regimes or unexpected events and things like that. Realistically, you want to be able to get to the point where you're pushing these models out with very little human intervention on sort of daily, weekly, hourly even frequencies, not twice a year. And then also, how's the performance monitored as well? If the data scientists basically train the models and then pretty much wash their hands of the affair, how do they know how it's faring? What is that feedback loop, right? Maybe the assumptions they made were wrong. Maybe they're not seeing the lift they expect. They can maybe infer that sort of an indirect sense from the data that's flowing back into the Hadoop cluster. But realistically, you want a much more direct feedback loop, especially if you're going to start pushing these things on a sort of hourly basis. And so, we've been thinking about this a lot at Alpine Data and trying to understand how we could actually best serve and best accelerate this. And so, we have a software process that's supported by our Chorus software that basically is this end-to-end, moving from sort of problem inception through to actionable results. And really, if you think about it, if you've seen part of this already, I should say, on the second slide, you saw the sort of visual workflow editor. In addition to that, there's a lot of other components. One of them is a sort of sophisticated project management and collaboration framework, because realistically, data science is not a solo sport. You need a team to actually perform that data science project. And so it starts off with sort of actually the business leader potentially defining the scope and the goals and the outcomes and basically giving the broader perspective around that project. You also then want him to be able to check in periodically to actually make sure that the project is moving forwards, right? That it's not sort of got mired down. You potentially also want domain experts who can tell you what the data means. Make sure you're actually understanding what the columns are. Too many times you sort of misinterpret that and things go off the rails. And then we start moving down what we like to call this pendulum down to the sort of transform stage where you're getting data engineers involved who are doing wrangling and cleansing and preparing the data for the project. And then there's the project, the stage that most people focus on, which is the modeling stage, where data scientists get involved and are building out these predictive models. And unfortunately, in a lot of projects that we see, people get stuck at this stage. It's sort of, almost the cult of the algorithm, where you're just sort of iterating and building more sophisticated algorithms, trying to boost your accuracy, but never going any further, never actually getting out to anybody benefiting from these results. So, at some level, it's fairly academic. So with the Alpine software, basically you push through the modeling phase and then in a turnkey way, without human intervention, are able to deploy your predictive models out to scoring engines that are basically located around your enterprise. And this can be done, as I said, in a completely automated, free from human intervention. Obviously, you can insert sort of governance and audit steps as appropriate before you start pushing models around. So then we have the deploy stage, and then the final is the act stage, which is realistically just connecting up these scoring engines to those business logic layers. So working with the customer to make sure that their Salesforce plugins talk to it and are leveraging the sort of scoring engine, that their Marketo is talking to it, that basically whatever web apps or web portals they've built are actually communicating with this and benefiting from the predictive results. And so now with this, we have the ability to very easily, in a seamless way, push out new models and update these scoring engines. And so this becomes a much more sort of frictionless cycle. We can also then start to build in responses from the scoring engine. So they're telling the data scientists about the efficacy of their models, what the lift is, where the problems are, and then we can make an informed decision about whether it's worth investing more time in the modeling stage. Maybe we're getting the benefit we expect. Maybe we want to actually, go to a more sophisticated model because it is going to pay dividends. And so it is a much more informed and sort of iterative approach to the current approaches to data science. And so you end up with something that looks like this, and basically, software trying to bridge the gap between the training of models on big data infrastructure and then pushing the scoring engines out to these sort of, microservices running on these PaaS solutions, be that AWS, Cloud Foundry, or Google Apps, or Docker, or whatever that may be. And sort of, in our case, we use our core software to bridge that gap. And so, again, in a turnkey way, we're able to take the models built even on traditional databases or Hadoop clusters and then push them out. So we work, obviously, with pretty much every flavor of Hadoop and database. But today, we want to talk about how we work within the pivotal BDS ecosystem. And so we have a very tight integration with some of the high-performance SQL solutions that Pivotal provides, both on the Greenplum side and then also on the HAWQ side. And there's a lot of sort of SQL wannabes in the Hadoop space. Most of them are not particularly performant. Most of them are not particularly complete or robust. But actually, HAWQ does a very good job of providing sort of comprehensive SQL support. So we can basically leverage those as data sources. We can push down SQL to those. We can actually train predictive models on top of that, either in SQL, or we can use Apache Madlib, which is basically C++ optimized implementations of sort of key machine learning algorithms like random forests. We then keep these models in an internal representation. It's a fairly rich representation of the model that allows us basically to oscillate almost between HAWQ and Greenplum. So you can train on HAWQ, score on Greenplum, and vice versa. And in some cases, we've seen actually that's the level of operationalization that customers want. Basically, they're putting all of this sort of historical data into the Hadoop cluster, training the models there, and then sort of at a nightly or weekly basis, they're scoring their sales leads, which appear in their Greenplum database, and then pushing out those results to the sales folks on a sort of weekly or daily basis. To take this one step further then, is to bring Cloud Foundry into the mix, right? Essentially, even though some people will want to score in their Hadoop system using, Spark streaming, using Samza, using Storm, the majority of instances we've seen, you do need to move it outside the clusters where you trained when you trained your data. And so basically, one solution to this is these standalone scoring engines. Realistically, you want them to be able to stand them up. You don't want to be messing around with sort of VMs and all that kind of stuff. You just want very, very lightweight scoring engines. You can stand up. They're easy to deploy, to maintain, to update. And ideally, as well, they sort of scale up and scale down in response to the dynamic instantaneous load. The nice thing is that Cloud Foundry provides a very elegant way for us to be able to do that. It's extremely simple to build a sort of basic scoring engine, wrap it, upload it, have it there, and then start pushing models straight up to that. And then it will respond dynamically to the real-time load that's placed upon it. The final piece of the puzzle then, realistically, is how do we represent those models, right? We can certainly do it using sort of our internal format, but it's nice to use open standards wherever possible and not create a sort of walled garden. And so the de facto way of doing this for the longest time has been PMML, predictive model markup language, created in '98, and I actually had to update my slides today because I noticed they just released the 4.3 version. They've been at 4.21 for a long time, and I think the press release came out yesterday, so then they're bumped to 4.3. It's actually pretty good for representing most common analytical models. If you've got a neural net or a random forest, it's very good at representing that. Where it's starting to show its age a little bit is in complex data preprocessing, right? We're not really taking the raw data and applying that directly to the predictive model. Think about the complexity of training, all the feature engineering that goes on before you actually apply it to the model, right, to really sort of get the best out of that model, the most accuracy, so to speak. There needs to be an analog of that on the scoring side. And so we're seeing a lot of scoring flows that are actually fairly complex with a lot of pre-processing. Basic pre-processing can be handled by PMML, but in a lot of cases, this is just too complex. And so you end up with basically a sort of companion script or code fragment that's actually doing the data pre-processing before you pass it to a PMML model. It works, but it's not optimal from a sort of enterprise standard, keeping it all in sync. How do you test it? Maybe this is hand-rolled code. Maybe you're getting mismatches between the versions. So there's a lot of opportunity for error there. The good thing is there's a lot of broad PMML support across the industry. Most things export PMML for at least a few of their models. Very few people actually import it, and I think this is, again, testament to the fact that everyone's focused on training the models, not really operationalizing the models. And so basically you end up with a situation like this, where this is actually a flow that's getting run on a scheduled basis every night. And it's not training the model. The model is being trained in a different flow. And this is conditionally pushing the updated model out to the scoring engine that's running live in Cloud Foundry. So you can see up at the top right, we're loading the model. We're then applying a bunch of test data to this model. We're looking at the prediction accuracy. And if it passes, we then push it out to that Cloud Foundry scoring engine. No manual intervention. Basically, this is an automated process where the models are retrained each night on the new data. We validate the correctness of the models, the accuracy of the models, and in an automated way push them out to Cloud Foundry scoring engines. Again, if the error turns out to be too high, we don't update it with a bogus model. We alert the data scientists who can come in and fix it. So what does this look like in real life? Well, basically, we're managing all our Cloud Foundry scoring engines from a single pane of glass. Very easy to stand them up, bring them down, modify them, scale them up, scale them down. You then simply configure in our software basically the name of the model you want to push and the URL of the scoring engine. That's it. It gets invoked overnight, automatically gets pushed. In this case, this demo actually is focused on RESTful scoring engines. So basically, you can start pinging it with curl or what have you. So this is, again, getting towards a fairly elegant way of pushing out your models and actually making them available to these end users so you can actually incorporate them, as we're saying, into the sort of web apps and sales sources and things like this. The one problem left to solve really is we a little bit have this sort of hokey solution where we've got these hand-rolled scrolling flows in addition to a PMML model. And that's pretty much what happened to support that scoring flow that we saw the data pre-processing is being done externally to PMML. So that's a little bit of a pain. The good news is that this has actually been noted by the industry as a whole, and the data mining group is working on the successor to PMML. It's called PFA. We're up to version 0.81 at present. It's fairly stable. It's maturing fast, and I think it shouldn't be too long before we hit version 1.0. And it's a significant step forward. I mean, as we said, PMML was created in the 90s. It served us well, but it's time for something new. PFA, to my mind, represents that, and very, very significant flexibility in how you can represent data pre-processing using PFA. And so I think the promise is really there of being able to encapsulate an entire scoring flow in a single PFA document. And so what does that then look like? Well, this starts to look like, again, so this is a more complex scoring flow that we have here at the, let's see what sequence, this is the entire scoring flow. At the top right, we have the model that's being imported. This is all the pre-processing. And then basically, we want to capture that entire flow and push that out automatically as a single document. We can already do that at present using sort of Alpine internal model formats. But again, we strive for open standards, so we're currently working on a PFA implementation that should be coming in future releases. And it's not a minor undertaking in the sense that you don't just want to take your model operators and allow them to export PFA. That really doesn't advance the conversation if in addition to being able to export PMML, for, say, logistic regression, you can also export PFA. What needs to happen is each of the operators that you support in that visual flow needs to have a corresponding PFA representation. And so basically, once this DAG has been created, this analytical flow, you can walk that flow, extract each of those PFA fragments, and then synthesize a single PFA document from that that can be pushed up to these scoring engines running in Cloud Foundry. The good news is that PFA is actually capable of representing most of the core sort of transformation operators that you want to do. It's much, much richer than PMML. There's going to be a couple of corner cases with some of the more exotic algorithms that you'd want to apply, so as transformations. But it really is the inverse of PMML, where it was only a limited set of operators that actually had an analog in PMML. PFA really focuses on this notion of PFA engines, single input, single output, and you can chain all of these together. And so it fits very well with this notion of these visual flows and these DAGs, especially if you have a simple sort of linear chain. Where it becomes a little bit more convoluted is if you have sort of complex DAGs of joins going on and things like that. It does take a little bit more to understand how to synthesize a PFA solution out of that. The other cool thing that's recently been added to PFA is this ability to supply sort of sideload supplemental information, right? So you can actually externally invoke UDFs in the PFA engines. And so you can imagine you've got a situation where you're sort of scoring, say, stock ticks. You've got a stock tick coming in, you're going to make a prediction up or down. And you want to provide environmental information to your scoring engine. You know, what's the NASDAQ trend? What's consumer sentiment and things like that? And so they provide the ability to actually supply this to the scoring engine dynamically, rather than you having to sort of reformulate your model every time you've got a new prediction about the market. And so I think we're finally getting to the point with the evolution of PFA where basically we can come up with a sort of comprehensive turnkey model operationalization strategy, right? Which I think will hopefully advance where we are in terms of sort of operationalizing data science, excuse me. And so really just to conclude, we've talked about obviously the importance of data science, but a little bit of the myopic focus on training and building complex algorithms on large data sets. And the overlooked component is, what do you actually do with those models when you have them? How does that change? How does that translate into action? How does that actually benefit the enterprise that you've created these models? To solve this, at some level, you really need an easy way to break those models out of the Hadoop data lake that sort of sat somewhere in the bowels of the basement, right? And move it closer to the point of use so it can actually be consumed by those business logic functions. Traditionally, this has been fairly tricky with PMML just because you did need sort of helper code and things like that, and it was a little bit more error-prone. It's certainly doable, as we've demonstrated, but I think the good news is that PFA tightens that cycle up very significantly and will make it almost seamless to be able to push out even complex scoring flows. And then finally, we illustrated how sort of Alpine's technology works seamlessly with Pivotal big data suite to actually allow sort of turnkey model operationalization without human intervention. And with that, I'll conclude and open for questions. So it's basically a stateful scoring engine, right? So, it's doing more than that. It's doing the PMML scoring. It's a sequence of PFA engines, right? So that's running in the cloud. Basically, what you're doing is you're uploading the sort of PFA specification which is really just telling the scoring engine how to basically formulate that flow. We're exposing a sort of RESTful interface, or you could hook it up to a Kafka stream or something, right? But essentially the logic that's being deployed to Cloud Foundry is the entire scoring solution, right? And that can be multiple different engines, and you've probably got some database backing there that sort of is stateful, such that you can persist multiple models, different versions of the models, and actually it's collecting performance metrics about what people are doing, the frequency of use, and things like that as well. So it's a fairly sophisticated thing that's actually being deployed and reporting back to the sort of data scientists about how it's being utilized. Mm-hmm.
You see yourself other data kind of like technology. One of them is Spring Data Flow,
Mm-hmm.
and then the other one like is compute like Spark. Because I see yours from the ETL visualizing is really powerful. I get a lot.
Mm-hmm.
But I kind of wish that you see that in other ecosystems a little bit more, like the next layer of abstraction.
Yeah, no, I mean, it's a good question. So, I mean, I think we focused today more on the sort of SQL side to sort of align with HAWQ and Greenplum. But, we support operators that back down onto Spark and things like that, right? And so a lot of our technology there is focused on sort of what we call auto-tuning, in a sense that, a lot of the default settings in Spark tend to be suboptimal. So we're sort of leveraging information. If you think about it, right, because you're dragging in operators that have been created by Alpine, right? We understand the performance characteristics of those operators in great detail. We also understand the size of the data that you're pushing in. And so we can do a lot of sort of real-time calculations based on the configuration of your cluster to really fine-tune your Spark job, right? So we can go out and look at, like, how much space is left in the queue, how much resources are you allocated, do we want to go with a small number of executors, or we're fairly memory heavy on things like that to basically accommodate the sort of load on the cluster. So you'll see a lot of times that Spark will sort of get stalled waiting for all the resources to become available. And so we work around that, because if you think about it, there's not a single optimal Spark configuration, there's multiple. And so we try to choose the best one that's suited to the real-time conditions on the cluster. Essentially, right, it's a layer of logic on top that's basically trying to decide how best to do it. Cool. Well, thank you, guys. I appreciate your attention. Let's go get beer. All right.